In this video, we apply the second translation theorem in the solution of an initial value problem. Here we're given y double prime plus y equals f of t, and f of t is a piecewise function, and then we're given some initial conditions. So this is our initial value problem. Notice that y of 0 and y prime of 0 are given, so the Laplace transformation method is appropriate here. And I told you that we're going to use the second translation theorem. Let me just remind you of what that says. It says that if you're taking the Laplace transform of f of t minus a times the Heaviside function at t minus a, it turns out that what you get from that is e to the negative as times the Laplace transform of f of t, which is otherwise known as f of s. So that's in the forward direction. Now, we also derived an alternate form of this. We said if you just have some function of t times the Heaviside function at t minus a, you're going to get e to the negative as, not times the Laplace transform of g, but times the Laplace transform, of g of t plus a. Now, a lot of students think that these are not equivalent to each other, but I think you can tell that if you make a substitution, if u is equal to t minus a, and then you solve that for t, and you make a substitution, well, this is exactly what you end up with here. So we can use either one of these when we're using, we want to use the second translation theorem in the forward direction. And then of course we can use this one backwards if we want to take an inverse transformation. So if we see an e to the negative as times the function of s, we know that the inverse transform is going to involve the Heaviside function. Now it turns out that the way you compute this over here is first you need f of t. So we'll take the inverse transform of f of s. That's going to give us f of t, but then we want to replace the t with t minus a. And then you're going to take all of that and multiply by the Heaviside function at t minus a. Now this piece is just f of t minus a times the Heaviside function at t minus a. And this notation that I'm using is not standard notation. It's just notation that I made up to make it easier to state these equivalent expressions. Or I guess I want to say, is it equivalent expressions or equal expressions? Equal expressions is appropriate here. We think of equivalent equations and equal expressions. All right, so those are the theorems we'll apply. But in order to do this, we need to start by writing that function f of t in terms of the Heaviside function. And we know we want to write it in terms of the Heaviside function because it's a piecewise function. So I would start there. Well, f of t is initially equal to 1. So whatever your function starts with at t equals 0, you want to write that down. Then we turn off the function 1 at t equals pi over 2. So we're going to subtract 1 and multiply by the Heaviside function evaluated at t minus the time when we're turning this function off. Since we're turning this off at pi over 2, we subtract the function and we multiply by the Heaviside function at t minus pi over 2. Then at that time, we're also going to turn this function on. So that means we're adding sine of t times the Heaviside function at t minus pi over 2. And you can check this for yourself. This is equal to this. If we're on the interval from 0 to pi over 2, remember how that Heaviside function works. It's 0 until you get to pi over 2. And then at t equals pi over 2, it jumps up to 1. That is the graph of the Heaviside function at t minus pi over 2. So that's the t-axis right there. So if I'm on the interval from 0 to pi over 2, we get 0. So I'd have 1 minus 0 plus 0, which is of course 1. Now, if I'm on the interval from pi over 2 to infinity, which is the second interval, the Heaviside function is 1. So this says 1 minus 1 plus sine of t. Well, 1 minus 1 is clearly 0. Then we add sine of t and we get sine of t. So this is another way of writing that. So we can write this way. Okay, that's the plan. And now this will be the right-hand side of our differential equation, and we can start solving the initial value problem. Now, I always like to start solving an initial value problem by telling the reader what my notation means. The Laplace transform of little y will be denoted by big Y. I'm curious what other professors use. I'm sure that they don't say little y and big Y. They might say lowercase y of t and capital Y of s. And it's just a lot of words. It's so unnecessary to me. But I've got little y and big Y, and the Laplace transform of little y is equal to big Y. And we'll start there. And then we take the Laplace transform of the differential equation. And I always start there because I don't like it when people just start using notation without telling you what it means. Okay. Now, the Laplace transform of the differential equation looks like this. We have the Laplace transform of y double prime plus the Laplace transform of y equals the Laplace transform of f of t, which is 1 plus sine of t minus 1 times the Heaviside function at t minus pi over 2. That's because our Laplace transform is a linear operator that we can just apply the Laplace transform to each piece, and then we can factor out that piece if we want to. Okay, so we can compute the Laplace transform of this now. N is equal to 2. That means when I'm computing the Laplace transform of that second derivative, I'll have 3 terms. We always have one more term than the order of the derivative. And it's going to have an s squared, and then we have an s to the first, and then we have an s to the 0. And then each of these terms has something multiplying it. And the first one has the Laplace transform of this function little y multiplying it. And then the order of the derivative increases as you go from left to right. So I have y of 0 and y prime of 0. And then we'll add the Laplace transform of y, which is just y of s. And then we have the Laplace transform of a sum. I could have said the Laplace transform of 1 plus the Laplace transform of that piece. The Laplace transform of 1 is 1 over s, and the Laplace transform of this requires us to use that second translation theorem. So I'm computing the forward transformation, and I don't have a function of t minus pi over 2 here. So I'm going to use this second version, the alternate form, and that's typically what's used, the alternate form of that second translation theorem for this piece. We're pattern matching. I'm calling this g of t, and I'm calling this h of t minus a. In that case, a is clearly pi over 2. So this Laplace transform of g of t times h of t minus a is equal to e to the negative as. So it's e to the negative pi over 2 times s times the Laplace transform of g of t plus a. So I'm replacing the t with a t plus pi over 2. Now, at this point, you could use the formula for the sign of a sum, like sine of a plus sine of b, and you could use that identity from trigonometry. You could also just look at the graph. Since we're shifting the sine graph by pi over 2 radians, that's going to be related to cosine. So let's think about how that would change it. The sine graph looks like this. It's equal to 0 at 0 and pi and 2 pi. If I shift that, or if I add pi over 2 to the t inside, what that's going to do is it's going to shift the whole graph pi over 2 units to the left, not the right, to the left. Sometimes it's counterintuitive. So it's going to look like this. And now you want to imagine continuing that, and you ask yourself, what does that graph look like? Do you see it on the interval from 0 to 2 pi? Can you see that that's cosine? It starts at 1, then it's 0, then it's negative 1, then it's 0, then it's back at 1. So we see just from graphing that the sine of t plus pi over 2 is equal to the cosine of t. That's one way of doing it. Or again, you could have used this trig identity the sine of A plus B is the sine of A times the cosine of B. I believe it's minus the sine of B times cosine of A, if I'm remembering correctly. And I might be remembering incorrectly. Oh, I just looked it up. Sine has a plus sign here. And actually, I should have remembered that because sine of 2a is twice an expression that looks like this. So yeah, there's a plus sign there, not a minus sign. So in this case, if I wanted to use this trig identity, I could. Sine of t plus pi over 2 is sine of t times cosine of pi over 2 plus sine of pi over 2 times cosine of t. And cosine of pi over 2 is 0, and sine of pi over 2 is 1. And so we get cosine of t. So if you prefer to look at trig identities, you could use this to get from here to here. Or if you prefer to look at graphs, and I prefer to look at it graphically, I would just think, okay, well, what happens if I take this sine graph and I shift it negative pi over 2 units that way? Or, you know, if I shift it pi over 2 units to the left, well, then this is what I get, which is, if I continue it, I can see that it's a cosine graph. All right, so when I'm taking the Laplace transform of this, I don't have a Laplace transform of t plus a constant in my table, but I can say, well, that's the same as cosine of t. And I do have the Laplace transform of cosine of t in my table. So we'll do that. And we should also substitute in our initial conditions. Y of 0 in the problem statement was given to be 1, and y prime of 0 was given to be 0. So after that little aside, we have this. We have s squared times y of s minus s times 1 minus 0 plus y of s is equal to 1 over s plus this exponential times the Laplace transform of cosine of t, which is s over s squared plus k squared, k is 1, minus the Laplace transform of 1, which is 1 over s. Okay, now we're trying to get s, or y of s by itself. So we state what our notation will be. We take the Laplace transform of the differential equation. We substitute the values of y and y of 0, or y of 0 and y prime of 0 is what I meant, from the initial conditions. And then you're down here and you just want to solve for y of s now. You want to solve for the transform of the function that you're looking for. So this is just a little bit of algebra from here. So I want y of s by itself on this side, so I'll add s to both sides. I'll also factor out the y of s. So I have s squared plus 1 times y of s here. And if I add s to both sides, I end up with s plus 1 over s plus this exponential times this expression here. And I'm going to leave my parentheses so it's open and beyond that point, because I know I'm about to multiply by this, or divide by this. In order to get y of s by itself, we need to divide every term by s squared plus 1. It's really dividing both sides of the equation by s squared plus 1. So this s I'll divide by s squared plus 1. Now for this one, I could divide by s squared plus 1, but remember that's the same as multiplying by 1 over s squared plus 1, so it just gives us an s squared plus 1 in the denominator. Since this is already a fraction, I'll multiply it by 1 over s squared plus 1, and I'll do the same thing here. That's 1 over s squared plus 1. So if I simplify, this becomes this. We have y of s equals s over s squared plus 1 plus 1 over s times s squared plus 1 plus this exponential times s over s squared plus 1, quantity squared, minus 1 over s times s squared plus 1. Now this is in our table, and this is in our table, but this s times s squared plus 1, I don't believe that that's in our table. Actually, let's check and see if that's in the table. If it's in the table, we'll just use the table. If it's not in the table, we'll use partial fraction decomposition to rewrite these guys. Okay, so I'm looking to take the inverse transform. So I'm looking in this second column, the right column, and I'm trying to get from the right column to the left column. So I'm looking for s times s squared plus k squared with a constant in the numerator, and that s times s squared plus k squared in the denominator. Oh, well, look at that. That was sort of surprising. I didn't expect to see that, but I see it right there. You see it? I was looking for s times s squared plus k squared. This one has an s times s squared plus 4k squared. That 4k has to do with the fact that this is a sine squared. But notice you've got a constant in the numerator, and we've got an s times s squared plus a constant squared, which will work with what we have right here. So I'm going to write this entry down from my table. So from table 9, or sorry, from the table, entry number 9 tells us that the inverse transform of 2 times k squared over s times s squared plus 4k squared is equal to sine squared of kt. And then this one was an s squared, or s over s squared plus k squared quantity squared. So let's look for that one as well. I believe I've already seen that. We've done that one together already. I think it's over here. Do you see it? There it is. So we have a 1s over s squared plus 1 squared quantity squared. So that matches this pattern. It doesn't have a 2 in it yet in the numerator multiplying that s, but it's just a constant times s over s squared plus k squared quantity squared. So the inverse transform of that is t times sine of kt. So this is number 22 from our table. We're just pattern matching, and then multiplying by well-chosen ones and adding well-chosen ones as necessary to match the pattern. Easy breezy. Okay, so we're here now, and we're going to use these two along with that second translation theorem. The inverse version of that says that if we have e to the negative as times f of s, the inverse transform or inverse Laplace transform of that is the inverse transform of f of s, which gives us f of t, but then we replace the t with t minus a, and then we take that and we multiply by the Heaviside function at t minus a. So we're going to use these three together to compute this inverse transform. I know what that one is, and that's going to be a cosine of t. And then this one kind of looks like this, and this is identical to that, except for it has a minus sign there. But this term, if we ignore the negative, is identical to that. So we can use this and this, or use this and this together to compute the inverse transform. Now we have to be careful here. This is a little different because it's not just a k squared, it's 4k squared. So we're saying here that 4k squared is equal to 1. So that means that k squared is equal to 1/4, which means that k is always assumed to be positive, and it's positive square root of 1/4, which is 1/2. So in the numerator, what I need is a 2 times 1/2 squared. 1/2 squared is 1/4. So 1/4 times 2 is 1/2. But I don't have a 1/2 up here. I have a 1. So I can multiply this by 1/2. That's legal, as long as I also multiply by 2. Because now that numerator is 2 times k squared. And if I take the 1/2 and I multiply by 2, that's going to give me the original 1. So I need a 1/2 up here as well. And I can compensate for that by multiplying by 2. 2 times 1/2 is 1. Okay, so that will allow us to take the inverse transform of this term and this term. And then this guy looks like this, where k is equal to 1 as well. So I've got s squared plus 1 squared. K squared is 1, so k is equal to 1. That means in the numerator I needed 2 times 1 times s. So I needed 2s up here. I can get 2s up there as long as I multiply by 1/2. 2 times the 1 over 2 is 1. So we're just multiplying by 1. Okay, so now I have everything I need to take the inverse transform of this piece, and then everything for this piece as well, and we'll have to use the inverse version of that second translation theorem here. So let's do it. Now we're ready. Y of t is the inverse transform of y of s, which is the inverse transform of this piece. Here we have k equals 1. That's s over s squared plus k squared, where k equals 1. The inverse transform of that is cosine of kt. Since k is equal to 1, it's just cosine of t. And then we have got 2 times this piece. So we're going to add 2 times the inverse transform of this. And the inverse transform of this is sine squared of kt, where k is 1/2. So we've got 2 times sine squared of 1/2 t, or you could write that as sine squared of t over 2. Then we've got this e to the negative as times this guy over here. So matching this pattern to this, I'm focused right here now. I know there's a lot of red, and it can be easy to get lost in this. I'm focused right there, and I'm focused right here. So in our case, a is pi over 2. Well, according to this theorem, we need to take the inverse transform of f of s, where this is f of s, and then we need to replace the t with t minus a, which is pi over 2. And then we multiply by the Heaviside function at pi over 2. So we will first compute the inverse transform of this. So that's going to be 1/2. And then the inverse transform of 2s over s squared plus 1 quantity squared, according to this, is t times sine of kt. Since k equals 1, that's going to be t times sine of t. And then we're subtracting 2 times the inverse transform of this piece, which we know from this is equal to this, where k is equal to 1. Or sorry, k is equal to 1/2 again. It's the same exact one that we used over here. So we have sine squared of 1/2 times t, which is the same as t over 2. And here t is going to be replaced by t minus pi over 2, and then we're going to take that result and we're going to multiply by the Heaviside function at t minus pi over 2. So now we've got this. So that's cosine of t plus 2 times sine squared of t over 2. And I want to replace my t's with t minus pi over 2 now. So you're going to have t minus pi over 2 divided by 2. All of that is multiplied by the Heaviside function at t minus pi over 2. Now you could simplify this further. You could say, okay, what happens to the sine graph when we translate it pi over 2 units to the right? Let's do that real quick. This is pi, that's 2 pi. And if I go pi over 2 units to the right, it's going to look like this instead. Well, that's like a cosine graph, but it's flipped. So this is actually negative cosine of t. Or you could use a trig identity to show that that's equal to negative cosine of t. You don't have to, but you can if you would like to. And we could do something similar with this, but I think it's just too much of a hassle. I'd rather not. We'll just leave it alone. We could also use a power reducing formula to write that in terms of cosine of t minus pi over 2. Ooh, actually, I kind of want to do that. No, it's beside the point in this class. So we can save that for your trig teachers. But you could write this in terms of cosine of t minus pi over 2 using a power reducing formula. Okay, so this is our answer. It's not simplified though. So I think I would like to write it as a piecewise function. Since I've got a Heaviside function of t minus pi over 2 here, this is a piecewise function with two pieces. One piece will have t between 0 and pi over 2. The other piece will have t between pi over 2 and infinity. So let's write our final answer that way. When t is less than pi over 2, the Heaviside function is 0. So we're just going to have cosine of t plus 2 times sine squared of t over 2. Now, on the other piece, the Heaviside function, that's when t is greater than or equal to pi over 2, the Heaviside function will equal 1 at that point. So we'll have this plus all of this. If you want, you could distribute the 1/2. I've got 1/2 times a negative cosine. I think I'll just factor out the negative 1/2. So I'll have negative 1/2 t minus pi over 2 times cosine of t. And then this is just a negative 2 times that sine squared of t minus pi over 2 over 2. So you could call that t over 2 minus pi over 4 if you wanted to. And of course, trig identities will help us come up with equivalent forms if we'd like. Now that is our function. If you take the derivative of that function twice, I know it's kind of strange. Take the derivative of that function twice. And whoops, where's the original differential equation? It's been a while. And you substitute into this differential equation and simplify. You're going to get f of t. And y of 0 equals 1, and y prime of 0 equals 0. So this is the function that solves this initial value problem. Again, the way we solve initial value problems with the Laplace transform is pretty simple. We introduce our notation, and we take the Laplace transform of the differential equation, solve for the Laplace transform of our solution, take the inverse transform to get little y of t back. In practice, there's a little bit more to it. If you've got a piecewise function, you've got to write that in terms of the Heaviside function first. And then these translation theorems are a little bit, can be a little bit tricky to apply, but actually remember the notation tells you everything you're supposed to do. If you understand what the notation is saying, then it's straightforward. It just might take a little bit of algebra and a little bit of time to do that correctly, and a lot of attention to detail. So that's the end of our example of using the second translation theorem in the solution of an IVP. I'll see you next time, and I think we're going to talk about the convolution next time.